Hello, here is a question. What is Hubble tension? So many of you have heard about it, Hubble tension and all these things, the cosmic tension. So we have to, in this video, we are going to focus on the Hubble tension and how we gonna elevate this Hubble tension systematically. So for that, I'm going to review one of the paper written by Christian Boehmer and et al. On the title is Dynamics of Dark Energy with Coupling to Dark Matter. So what does this tell you about this? So the thing is that we want to understand about the dark energy and which is directly coupled with dark matter. We will see in a minute that what is the meaning of this dark matter. First of all, let me just give you a brief idea about what is Hubble tension and why is this tension arising. So this is the minute, okay? So let us begin. Well, here I am showing you some kind of a data, and this data is the measurement of Hubble tension H0, and this is the H0 corresponds to today's value. Okay. Now here are two kind of tests. The test is called indirect test of Hubble tension and direct test. Now what is the meaning of indirect test? So when we are seeing our universe in the past, we have the several things. For an example, the cosmic microwave background and the recombination era. So the greatest evidence of our history can be analyzed through the CMB. Okay, so now what we can understand about the CMB. So CMB with the Planck observation, CMB without Planck observation, no CMB with BBN, and CMB lensing. So there are different set of data set, and from which we can understand so many things. Now CMB with Planck, so there is a Planck observatory. So what we have understood that here we can in x-axis what we can understand. Here you see that this is 60, 65, 70, 75. So therefore the pink color is corresponds to 65 to 70, and the yellowish color, the pale yellow color, is between 70 to 75. Okay. Now here is the indirect test when we are understanding about the Planck data. So what we are getting is that when we are trying to understand the CMB through Planck data or without Planck data, or without Planck, or maybe Big Bang nucleosynthesis. So what we are observing that these values, that the big bubble dots, are actually relying between 65 to 70. Can you see here? Yes. Okay. And when we are coming to direct test, now in direct test, when we are observing the supernovae, and from these supernovae, when we try to understand that how the universe is expansion. So this data is corresponds to the redshift, and when we are analyzing different supernovae like supernovae Cepheid, TRGB, and different there are so many things. Okay, what we are getting that these bubbles are actually falling on this yellow portion, and this yellow portion is actually giving you the 70 to 75, means that it is corresponds to 74 kilometers per second megaparsec. Okay, there is a huge difference. What we are here analyzing, that it is 65 to 70, and here we are getting is between 70 to 75. So why it is? And you may also ask that how we have got this data. Well, we have the very standard way to understand cosmology, how we are dealing with this. Suppose so Einstein has given his theory of general relativity, where he said that from the Einstein-Hilbert action you have this kind of thing, and he said that okay, you can add one more constant which is acting as a cosmological constant, and now you have the some kind of an matter component, and take the universe to be like FLRW metric. Okay, so universe is isotropic and homogeneous, and from here you will get two Friedman equation like h square is equal to 8 pi g over 3 into some kind of radiation. You have some kind of an matter, let us say baryonic fluid you have, and then cold dark matter and the dark energy relation. And after that, what you can say that here we have the second Friedman equation, 3h square is equal to some like 8 pi g. Some pressure corresponds to these guys, like baryon pressure, radiation due to dark matter, and pressure of this cosmological constant. Now, if you will analyze this cosmological model, this is called the model, and whatever we are observing, okay, whatever you are observing the Hubble Hubble parameter, we have to assume the model, and this is the so far the best model we have, okay, and from which we are analyzing the data. So our model is not changing in the two ways, like either you are doing the indirect observation or the direct observation, your model is not changing. So what is changing? The way we are measuring. So we have two methods, the way we are measuring, indirect methods and direct methods, and what we are getting is surprising result. And now this has begun the tension among the cosmologists that why this thing happens. Well, one may say that this may be some kind of an statistical, conflict, that maybe if you will take more and more data, therefore the gap will, surprisingly come closer, and there may be some kind of, we will get that there is no any Hubble tension and the gap is very small, and Hubble tension or the Hubble rate could be 70 kilometer per megaparsec per second megaparsec, okay. But what is surprising is that as we are getting the data from the CMB and the supernovae, this gap is basically increasing, and this gap is extremely increasing, that scientists say that something is happening which is, we cannot understand from this lambda CDM model or whatever the existing physics we have. It means that there is new physics is going on, and that is the conflict, and this conflict is called the Hubble tension and nothing else. There is not too much very big deal, but from the scientific view it has a very big deal. So what are the ways in order to understand this Hubble tension? Well, there are surprisingly so many ways, but we don't know which one is true. Okay, so let us just first of all let us try to understand what could be the different ways. Okay, so I am presenting you some very interesting point of view to how can we understand about it. Okay, so now here we have seen that, okay, our theory is governed by, let us say, Einstein equation. This is corresponds to Einstein equation, and we are assuming whenever I'm writing kappa square is corresponds to 8 pi z, and then we can understand that there is some kind of a fluid. Okay, there is a perfect fluid. So in our universe has begun from the radiation, and then there is a matter, and then there is a dark matter, and there is dark energy. So radiation has the density is evolving, it is kind of 1 minus 8 to the minus 4, 8 to the power minus 4. Okay, and here the matter part, the baryonic density is falling with 8 to the power minus 3, and similarly similar situation happens with the cold dark matter, and the radiation with this is happen to be 8 to the power 0. So the dark matter radiation is kind of very constant. Modeling things like there is a fluid corresponds to radiation and matter fluid, and this matter is corresponds to baryonic matter and as well as cold dark matter, and we can add another fluid, let us say this is 1 and this is 2, and this corresponds to a dark energy. Now this fluid has a very interesting property. Okay, now this fluid have the interesting property in such a way that it has the negative pressure. The pressure is come out to be negative. Okay, now here if you have ordinary fluid, we can write is P is equal to omega of rho, and rho is the energy density of the fluid, which cannot be negative, which is true in the dark energy case. So well, we are seeing that if you have the fluid which is baryonic fluid, or the fluid we are seeing in the earth, the pressure is coming out to be positive. Okay, now we have the special kind of fluid which pressure is the negative. So what we have to do in order to get the pressure to be negative, we are saying that this omega could be negative. Okay, and it came out from the observation that is omega have to be like less than minus 1 by 3. It means that you can have like minus 0.4, minus 0.6, minus 0.9, or let us say minus 1, or maybe minus 1.2. We will talk about these data later on. Okay, so what when we are analyzing these situations, okay, so in the lambda CDM model we are treating this SM2 will be just like fluid, and we are calling it the lambda CDM model. We have the constant density there, rho is equal to simply lambda constant energy density. Okay, so when we are everything model in terms of fluid, it came out to be that H0 has some kind of a property. From indirect we are getting like 69 or 60, let us say 68, or if direct we are getting like 73. Now there are so many ways. We have already uploaded so many videos, like there are so many fields, okay, which can depict dark energy. For example, the quintessence, the k-essence, okay, and there are some kind of vector forms of fields which can actually depict the debit the dark energy, and we have kind of a modified gravity. So we can easily modify our existing gravity, and we are saying that there is nothing like dark matter and dark energy. It is the one of the property of space-time, and through which we can get the acceleration. But so many FR models have been discarded because against the data, because it cannot so many other like gravitational lensing phenomena, something like CMB spectrum. It is they are not obeying. So many models of FR model have been rejected. So these are the problems. Now, if you are replacing, if you can replace SM2 by some of the fields like phi, X, let us say we are talking about Chaplin gas and so on. Now again, the problem is that if you are still testing it against CMB and supernovae data, they cannot elevate this Hubble tension. They demand more. Now, what this Hubble tension requires, this Hubble tension is the equation of a state. If you don't know about equation of a state, you can check out my video. The link is here. The equation of a state is crossing this -1, which says that the universe is giving the more acceleration. Okay, so this is called the phantom situation, the phantom regime. The universe is crossing the negative of -1. So when you are testing, when you are using this kinetic kind of model of dark energy, or the quintessence kind of model, their equation of state actually converging to negative of -1. It cannot cross it. So therefore, if it is not crossing it, so we cannot have this elevation of H0. Now then what we can do? So in order to do that, what we can see here, that okay, we are not disturbing the space-time curvature. Okay, space-time is still given by gravity. This one, Einstein gravity. Einstein's theory is completely correct. What we can do is that we have dark matter and dark energy. And if we have the dark matter and dark energy in our system, what we are getting is that rho dot is equal to -3h rho plus phi for dark matter, and simply rho phi is equal to -3 rho plus p. This is called the conservation of energy. Now in the expansion of the universe, because this is positive, and with time their energy density is falling, and if they are actually connecting like this, like if you are adding everything in terms of like this, any algebraic coupling you have, we can say that these guys are talking with each other minimally, means that they are only evolving with the space and time. They are not talking in another way. Okay, so what we can understand, that suppose this is the fabric of the universe. Okay, this is the universe, and here you can have the dark matter. So there is a devolution in dark matter, and we can have the evolution in the dark energy. And they are actually talking with how the space-time is actually evolving, or how they are disturbing. They will talk like this. Okay, and there is no any way it has the direct interaction with this thing. So what we are understanding, that we are not changing the background curvature of here. There is no any direct influence of the curvature, manipulation of curvature on the fields and fluids, like it is called the minimal coupling. So what we can say, that these two guys here, they are dark, and maybe they have some kind of a direct connection. So what we can do here, that keep this form like this. Here is Sm and here is S phi, the field equation, and introducing some other parameter, and it has some component of dark matter and dark energy. Now if you have these kind of scenarios, what you will get is that they are not talking with each other, and still these guys are actually minimally coupled with the fabric. Means that space-time, means that if space-time is evolving, they will always evolving, but now they have the direct interaction between them, that if something is changing here, it will gonna affect here. If something is going to be here, then there will be effect. So this is called the direct coupling, or called interacting dark matter and dark energy. Okay, so I hope this concept is clear now. In order to understand more about it, so in 2008, Christian Boehmer have written this paper called Dynamics of Dark Energy with Coupling to a Dark Matter. Now this is a very interesting paper. Why? So whenever you have this kind of scenario, like S is equal to R square root of -g d4x plus some kind of an perfect fluid, and plus some kind of an field, what you are actually getting is that the Hubble parameter is corresponds to kappa square into rho total, whatever the energy density you can add, and then 3h square plus over the again 2h dot is equal to minus kappa square, again p total. Okay, now there is a more interesting portion is here. You have the conservation equation, and whatever the components you have added, they are individually conserved. Means that if you are adding the cold dark matter, they have this property like rho plus p is equal to 0, and if I am adding this rho phi dot 3h, rho phi plus p phi is equal to 0. They are conserved separately. We already understand that from the Einstein equation, G mu nu is equal to kappa square T mu nu, and from the Bianchi identities, this holds true like G mu nu is equal to 0, and from their observation we are saying that this T mu nu is equal to 0. Now when we are saying that these two guys are actually talking to each other, so what we can instead do is that they are not separately conserved. There is some kind of a term existing here like minus q and plus q here, which is causing the direct transfer of energy between them. So now they are not conserved. So but we understand that del mu g mu nu has to be 0 and del mu t mu nu has to be followed. So we can say that individually their energy momentum tensor is not conserved, but their total energy momentum tensor is still conserved. Okay, so now this term we have added a q. U is the interaction term, which is happening that the energy density is actually transferring from one fluid to another. This negative sign said that some energy is transferred from dark matter to dark energy, and this plus shows that if you have the positive q and this is positive, then it is taking energy, and if it depends on you. If q is coming out to be positive, then it says that this is actually taking the energy. So it depends that one way or another, one is releasing some energy, another one is consuming energy. Okay, it always depends on how your q come out to be, but you have to add like this, that minus q plus q has to be 0, so that our energy momentum tensor is going to be 0 always. Okay, so this is called a direct coupling between two components. Now we want to understand the dynamics of dark energy, and for which they have talked about they have taken the field of quintessence, and they have taken some kind of a perfect fluid for dark matter. And you know the property of dark matter, that the dark matter is the pressureless fluid. Okay, and you already know, we have already talked about that, but this guy del mu phi minus of v phi. Okay, and this v phi is coming out of half m square phi square kind of thing. Okay, and we can model it. So this is kind of a quintessence, and considering this is not the case, we can always change the potential. So this is the quintessence action. Okay, and this quintessence action corresponds, this is the s phi. Now for this task, they have considered the v phi to be v naught exponential minus kappa lambda phi, and lambda is some kind of parameter, and v phi it is the dimension of m to the power 4. Now when they have talked about the dynamics, now dynamics means that we want to understand about the dynamical feature of the scalar field and the fluid field. So they have studied in terms of a dynamical variable, which you can understand more about it. We have already talked about in this channel. Just click on the link, that how we can understand about the dynamical stability of the system. We will deal more about it in a later video. So thank you very much. See you later.